Alright, so hello, my name is Jeff Hutchinson. My presentation today is about the Electronic Numerical Integrator and Computer, also known as ENIAC. ENIAC was the first general-purpose computer. It was developed by the Moore School of Electrical Engineering at the University of Pennsylvania at the request of the U.S. Army's Ballistic Research Laboratory, or the BRL. At the time, the BRL was receiving requests to complete 40 firing tables per week when they were only capable of doing 15. Each firing table would take a single person 20 hours to complete using only a desk calculator. The same table could be completed using an electromechanical differential analyzer in 15 minutes. Once construction was complete, the ENIAC could complete one firing table in 30 seconds. Once constructed, ENIAC was 80 feet long and weighed approximately 30 tons. It was built from 18,000 vacuum tubes, 10,000 capacitors, 1,500 relays, 6,000 manual switches, and 70,000 resistors. It took approximately 5 million hand-soldered joints to construct the unit. The individual units within ENIAC could be broken up into 4 categories: arithmetic, memory, input and output, and governing. This list of systems in ENIAC is from a report detailing the work performed under the contract between the University of Pennsylvania and the U.S. Army. It shows the input was provided by an IBM card reader which read punch cards. Their information from the cards was stored digitally in the constant transmitter. From there it could be sent to other systems in the computer. Output was performed by a IBM punch card, or card punch. The system was governed by the initiating unit, the master programmer, and the cycling unit. The initiating unit was used primarily to start and stop the system. The master programmer was used when the program needed to branch or loop, and the cycling unit provided the pulse or signal to the other units for a synchronous operation. The ENIAC was not a stored program machine, meaning the program instructions were not stored on the machine. Rather than typing commands into a computer terminal, programming the ENIAC required setting thousands of switches and connecting hundreds of cables. It generally took anywhere from a couple days to a week to design the program, set the switches and cables, and debug the machine. Fortunately, the cycling unit could operate one cycle at a time for debugging purposes. The 3-wheeled objects on the right of this picture are the function tables. They were basically the equivalent of a ROM and stored constant values which could be fed into the other systems for performing calculations. ENIAC contained a very impressive 20 accumulators. Each accumulator was capable of storing a signed 10-digit number, or 2 accumulators could be combined to store a 20-digit number. Each accumulator was capable of receiving numbers from other units, adding received numbers to store numbers, finding the tens complement of a stored number, and transmitting the stored number or its complement to another unit. Subtraction was performed by adding the tens complement the same way today's binary computers perform subtraction by adding the twos complement. Digits stored in the accumulator were in decimal form. This was accomplished with the use of a decade counter, which is a ring counter with 10 flip-flops and 10 states. Each state represented a digit, and within that state, one flip-flop representing the digit would be on while the other 9 would be off. There were lights on the front panel indicating the value of the current state. When a signal was sent to the counter, it would advance to the next state. If it was advancing from the state representing 9, the next state would be 0, and a carry signal would be sent to advance the counter representing the next digit in the number being stored. There was also a binary ring counter to represent the sign of the number. Data was transmitted through what was called digit trays. Today we would just call it a bus. Information was sent in parallel using 11 lines, one for each digit and one line for the sign. And there were also program trays for transmitting instructions. ENIAC's high-speed multiplier handled all multiplication in the system. It was capable of performing up to 385 multiplications per second. The unit used one accumulator to store the multiplicand, one to store the multiplier, and either 2 or 4 accumulators to store partial products depending on the number of significant digits needed. This table shows the multiplication process along with the needed cycle times. Multiplication was performed as a series of single-digit multiplications, much like doing it on paper. The product of each smaller multiplication was found in a table in memory. The tens digit was stored in one accumulator, and the ones digit was stored in another. These partial products were later summed together to form a final product. The final piece of ENIAC is the divider and square rooter unit. This unit calculated all division and square root problems in the system. It was capable of performing 40 divisions or 3 square root calculations per second. Both of these were performed using algorithms involving a series of additions and subtractions. The non-restoring division algorithm for division and a square root algorithm based on the formula shown was used for finding square roots. Over the years, the modern computer has not changed much. It's become smaller and faster, but the basic architecture remains nearly the same. To see the changes in size and speed, one could look at ENIAC on a chip. In 1995, to celebrate the 50th anniversary of ENIAC, students at the University of Pennsylvania created a microchip with the same functionality as the original ENIAC. Measuring only 7.44 by 5.29 millimeters, it's 200 times faster than ENIAC and consumes 340,000 times less power. And that was pretty much it. Do you have any questions? Or
I don't have any questions, but I just want to say thanks for that presentation. I've read about the ENIAC kind of as an abstract thing a number of times in the past, and I sort of knew that it had to do with calculating ranges and stuff like that. But seeing the sort of the details of how it was broken down and how it actually worked is very interesting.
Thanks. It was the first I had ever heard about it was in our book, and then it kind of caught my eye that, well, let me find it. It says the ENIAC was a decimal rather than binary machine. So what exactly they meant by that kind of intrigued me. I wanted to learn more about it and see how the computers had changed since then. And like I say, and really they haven't hardly changed at all. Still have buses, and separate buses for data and instructions and all these different things. Still have flip-flops for registers and accumulators, and I mean I don't know. In some regards, it's almost odd that it's so similar to what it used to be. Like you would expect there to have been a lot of changes. But.
Right. I think a significant aspect of our advances has really just been figuring out how to manipulate matter in more sophisticated ways. We're still using the same kind of logical processes.
And a side note, something I forgot to throw in was that the ENIAC could compute 5,000 addition problems a second. So I don't know, that's just kind of what they based all of their timings on, like in the things I was reading. Rather than cycles per second or instructions per second, it was additions per second, or the other things that it could do were always timed in terms of additions. I just thought that was interesting. But
it is. I would imagine that if you tried to think of it in cycles, it probably would take an appreciable amount of time for a full cycle to process all the way through the whole room of vacuum tubes.
It wasn't, well, I guess by today's standards, pretty slow, but 100 kilohertz, I don't know, it was probably like lightning
Yeah,
fast for the time.
sure.
But